Welcome to this video in our generative AI series where we'll be exploring the key differences between discriminative and even generative AI. While both play essential roles in the order of machine learning, they approach tasks in very different ways. In this video, we'll break down what makes each model unique, how they work, and when you would use one over the other. By the end, you'll have a clear understanding of these two important concepts and how they fit into the broader AI landscape. Let's dive in. 1. Introduction. In machine learning, there are two major types of models that help us solve different types of problems: discriminative models and generative models. Discriminative models are like a skilled referee in a game. They focus on learning the boundaries between different categories so they can accurately make decisions. For instance, if we have a set of images of cats and dogs, a discriminative model would learn how to tell the difference between a cat and a dog by focusing on features that distinguish them. These models are typically used in classification tasks where the goal is to predict labels, such as identifying if an image contains a cat or a dog. On the other hand, generative models are more like an artist. They aim to understand their data so well that they can create something new that looks similar. For example, a generative model could be trained on images of cats and then generate entirely new images that resemble real cats. These models understand the underlying patterns of the input data and can generate new samples that fit into the same distribution. Generative models are used in applications like image synthesis, natural language generation, and data augmentation, where it's important to create new data or understand the structure of the existing data deeply. Understanding when to use each type is crucial. If the task is to classify data accurately, a discriminative model is usually the go-to choice. However, if the goal is to generate new content or understand how the data is structured, a generative model would be more appropriate. Both types of models have their unique strengths, and depending on the problem, one could be the perfect tool for the job. 2. What are discriminative models? Definition. Discriminative models are primarily used for classification and regression tasks. They learn to map input features directly to the target labels by modeling the decision boundary between classes. Essentially, they answer the question, given this input data, which category does it belong to? For example, a discriminative model might be used to determine whether an email is spam or not by analyzing its content and identifying key features that differentiate spam from legitimate emails. Mathematical perspective. Discriminative models are a type of machine learning model that focuses on distinguishing between different classes by estimating the probability of a label given the features of the data, which is mathematically represented as Px. Here E represents the label we want to predict and X represents the input features of the data. Essentially, discriminative models are interested in learning the boundary that separates different classes rather than understanding how the data itself is generated. How they work. Discriminative models work by identifying the patterns and correlations in the input data that are most closely related to the target labels. During training, they use a mathematical function called a loss function to evaluate how well the model is performing. The loss function measures how far off the model's predictions are from the actual labels are, and the model then adjusts its internal parameters to minimize these errors. This process is repeated until the model becomes good at making predictions. For instance, if a model is trained to recognize whether an image contains a cat or not, it will analyze the features of the images like the shape of the ears, eyes, and whiskers and gradually learn to correlate those features with the label cat. Each time the model makes a mistake, it tweaks its parameters to reduce the likelihood of repeating the same mistake in the future. This is how the model improves over time, ultimately allowing it to classify new unseen images accurately. Example. Imagine we have an image classification task where we want to distinguish between images of cats and dogs. A discriminative model learns to differentiate these two classes by focusing on the features that make them distinct. For example, it might learn that cats usually have pointed ears while dogs might have floppy ears. It could also use other features like the texture of the fur or the shape of the face. By analyzing these unique characteristics, the model is able to make predictions about whether a new image is of a cat or a dog. So, when you give it a new image, it uses the features it has learned to assign the correct label cat or dog based on what it has learned during training. The discriminative model's ability to focus on key features that separate the two classes helps it make accurate predictions for new unseen images. Common discriminative models. J. Logistic regression. This is a simple and effective model used mainly for binary classification tasks where the goal is to predict one of two possible outcomes. It models the probability of a class using a sigmoid function which outputs a value between 0 and 1, making it suitable for problems like determining whether a customer will buy a product or not. Support vector machine says VMS work by finding the optimal boundary or hyperplane that separates different classes in the feature space. The goal is to create the widest possible margin between classes, which helps make the model robust to noise. For example, spam could be used to classify emails as spam or not by finding the best boundary that separates spam features from non-spam features. Random forests, these are an ensemble of decision trees that work together to improve predictive accuracy. Each decision tree makes its own prediction, and the final result is often based on a majority vote. Random forests help to reduce overfitting, which can be a problem with single decision trees. They are commonly used in various applications, such as predicting whether a customer is likely to churn based on their usage data. Neural networks, these are complex models capable of capturing intricate relationships in the data. Neural networks consist of multiple layers of interconnected nodes, allowing them to learn deep and non-linear patterns. They are often used in applications like image classification, where they can learn to recognize different features like shapes and textures to identify objects in the image. For instance, a neural network can classify whether an image contains a cat or a dog by learning the distinguishing features of each animal. Applications. Spam detection discriminative models are used to classify emails as spam or not spam by analyzing the features of the email content. These features could include the frequency of certain words, the presence of links, or even the sender's email address. By identifying these patterns, models like logistic regression or support vector machines can effectively separate spam emails from legitimate ones. Sentiment analysis. In sentiment analysis, discriminative models are used to determine whether a piece of text expresses a positive, negative, or neutral sentiment. This application is commonly seen in analyzing customer reviews, tweets, or other text data to understand public opinions about a product, service, or event. For instance, a neural network might analyze customer reviews and predict whether the sentiment is favorable or critical. Fraud detection. Detecting fraudulent transactions is another common application where discriminative models are extremely useful. By analyzing transaction data such as purchase location, amount, and user behavior, the model can identify unusual patterns that may indicate fraud. Random forest, for example, can combine multiple decision trees to provide accurate predictions, making them well suited for identifying suspicious activities in financial data. Medical diagnosis discriminative models can also be used in healthcare to predict diseases borne patient data such as symptoms, test results, and medical history. For example, a support vector machine might be trained to classify whether a patient has a certain disease based on their test results, enabling doctors to make informed decisions. These models help in providing accurate diagnosis, especially in scenarios where early detection is crucial for successful treatment. 3. What are generative models? Definition. Definition. Generative models are a type of machine learning model that aims to understand the process behind how the data was generated. Instead of just focusing on distinguishing between classes as discriminative models do, generative models learn the joint probability distribution of the input feature and labels. This means that they learn not only the relationship between inputs and outputs, but also how the inputs themselves are distributed. By doing this, generative models can create new data points that resemble the original training data. In simple terms, they answer the question, if I know a category, how can I generate data that looks like it belongs to that category? Mathematical perspective. From a mathematical perspective, generative models focus on estimating the joint probability distribution of the features and labels, which is represented as Pxy. This means that learn both the distribution of the input data X and the labels Y, allowing them to fully understand the relationships in the dataset. Alternatively, they can also model Pxy, which is the probability of features given a particular label, along with Pi, which represents the probability of each label. By understanding these probabilities, generative models are capable of generating new examples that look similar to the training data. How they work? Generative models work by learning the underlying structure and distribution of the data that they are trained on. Instead of simply focusing on the differences between classes, they try to understand the entire dataset, capturing the patterns and features that define it. By learning the data's distribution, generative models can create new data points that are statistically similar to the original set. Now, for example, if a generative model is trained on thousands of pictures of human faces, it can learn the patterns that make a face look realistic, such as the positioning of eyes, nose, and mouth. Once the model has captured this distribution, it can generate entirely new images of faces that look like real people, even though these faces are not of anyone that actually exists. This capability is used in applications such as generating realistic images, synthesizing text that sounds natural, or even creating deepfake videos. Key strength of generative models is their ability to capture the richness of the data, allowing them to produce entirely new but plausible examples. Example: in the case of a cat-based dog classification task, a generative model does more than just decide whether an image is of a cat or a dog. It actually learns to generate new images of cats and dogs by capturing the patterns and pixel distributions that define each line. This means that instead of simply identifying the features that differentiate a cat from a dog, the generative model understands what makes each animal unique, such as the fur texture, ear shape, and facial expressions. By learning the distribution of these features, the model can create entirely new and realistic images of cats or dogs that look like they could have come from the training data, even though they are completely original. For example, if you ask the model to generate a picture of a cat, it would produce an image that has all the features typical of a cat, even though it has never seen that exact image before. This ability makes generative models useful for creating new content such as realistic animal images, and they are widely used in creators like art generation, video game design, and common generative models. Naive Bayes is a simple yet effective generative model that makes the assumption that all features are independent of each other, which helps simplify the quotation of the probabilities. Despite the assumption being rarely true in real world data, naive Bayes often works well in practice for tasks like text classification and spam detection. For example, it can predict whether an email is spam by independently analyzing the frequency of specific words. Hidden Markov models, HMM's hidden Markov models are used for modeling sequences and temporal data, making them particularly suitable for tasks involving time series or sequential events. HMS assumes that there is an underlying hidden process that generates the observed data. They are commonly used in applications like speech recognition, where the goal is to model sequences of words or sounds. For instance, HMMs can predict the next word in a sentence based on the hidden structure of the previous words. Generative adversarial networks, GANs are a type of generative model that consists of two networks, a generator and a discriminator, that compete with each other. The generator aims to create realistic data, while the discriminator tries to distinguish between real and fake data. This competition helps the generator improve until it can produce data that is nearly indistinguishable from real data. GANs are widely used for generating realistic images, such as creating new artwork or even generating realistic human faces. Variational autoencoders (VSVs) are generative models that encodes the input data into a compressed form coordinate space and then decode it back to reconstruct the original input. By learning to compress and reconstruct data, BIs can generate new examples similar to the original data. They are useful for tasks like image generation and data compression. For example, a weight trained on handwritten digits can generate new, unique digits that resemble those in the training set. Applications. Image generation generative models are widely used for creating new images, whether for artistic purposes, design, or data augmentation. They can learn from a dataset of images and then generate entirely new pictures that resemble the training examples. For instance, generative adversarial networks (GANs) are often used to create realistic images that look like real photos, which can be helpful for creating art, filling in missing parts of an image, or even generating synthetic training data to improve machine learning models. Text generation generative models can also produce human-like text, which is used in applications like chatbots or automated content creation. These models learn the structure and patterns of human language from large data sets and then generate coherent and contextually relevant text. For example, a text generating model can create responses for a virtual assistant or generate articles by understanding the pattern relationships between words. Anomaly detection generative models can be used to identify anomalies in a dataset by learning the normal data distribution and then identifying points that differ significantly from this distribution. This is particularly useful in areas like fraud detection, where unusual patterns of transactions can indicate fraudulent activity, or in monitoring industrial processes where abnormal sensor readings might indicate a fault. Speech synthesis. Another application of generative models is in speech synthesis, where they are used to generate realistic human speech from texting. By learning the nuances of human speech, such as intonation, rhythm, and accent, these models can produce lifelike voices, which are useful for virtual assistants, accessibility tools, and other voice-enabled applications. For instance, models like WebNet use generative techniques to produce natural sounding speech that is almost indistinguishable from real human voices. 5. When to use discriminative based generative models. When to use discriminative models. Discriminative models are best used when the primary goal is to achieve accurate classification or prediction. If your task involves assigning labels to input data, such as determining whether an email is spam or not, or predicting whether a customer will churn, then discriminative models are typically a great choice. They focus solely on the relationship between the input features and the labels, which often results in higher accuracy when classifying data. Another scenario where discriminative models are ideal is when you have a large amount of labeled data available for training. Since these models learn directly from the labels, having a lot of labeled examples helps improve their performance. Discriminative models are also preferred when computational efficiency is important. They generally require less time for both training and inference compared to generative models, making them suitable for applications where quick decision making is needed, such as real time recommendations on an e commerce website. Example Example In spam detection, the main objective is to accurately classify emails as either spam or not spam. Discriminative models such as logistic regression or support vector machines (SVMs) are well suited for this type of task because they are exactly on modeling the boundary that separates the two classes. Instead of trying to understand how emails are generated, these models focus on finding the features that most effectively distinguish spam from non-spam. For example, a logistic regression model might use features like specific keywords, the frequency of links, and the sender's email address to decide whether an email is spam. By concentrating only on the relationships between the features and the labels, discriminative models are able to achieve higher accuracy in classification tasks like this, making them a popular choice for spam filtering. When to use generative models? Generative models are most suitable when the goal is to generate new data samples, understand the underlying distribution of data, or when working in unsupervised learning settings. These models are capable of learning the structure of the data, which makes them ideal for tasks like creating realistic images, synthesizing text, or even generating new music. Generative models are also helpful when there is a scarcity of labeled data but an abundance of unlabeled data. Since these models don't necessarily need labels to learn, they can still capture the distribution of the data and make use of the available information. A common use case for generated models is in anomaly detection. By learning the normal data distribution, generative models can identify outliers or anomalies that deviate significantly from the usual patterns. For example, in fraud detection, a generative model can help detect unusual financial transactions and comparing them to the typical patterns it has learned. This makes generative models a powerful tool in applications where understanding the data and generating realistic samples are key objectives. Example, in image generation, goal is to create new realistic images to act as address and match up those found in the training data, and this is where generative models shine. For example, generative adversarial networks GANs are often used to generate human faces that look highly realistic. GANs work by capturing the complexities of the data distribution, such as facial features, lighting, and textures, and then using this learned knowledge to generate entirely new images of human faces. These faces look like they could belong to real people, even though they are completely novel and not copied from any specific training image. By modeling the full distribution of the data, generative models are able to create original and convincing examples, making them ideal for tasks that involve creativity, such as generating new characters for games or creating artwork. 6. Real world examples. Discriminative model examples, spam classification. A great real world example of a discriminative model is its use in spam classification. The main objective here is to classify incoming emails as either spam or not spam. To achieve this, the model analyzes various features of the emails, such as keywords commonly used in spam messages, the sender's information, and other metadata. Logistic regression is often used in this scenario as it can predict the probability that an email is spam based on these features. By learning which features are most indicative of spam, the model is able to make accurate predictions, effectively filtering out unwanted emails. This helps ensure that users receive fewer spam messages in their inbox, significantly improving their overall experience. Generative model example, image generation. A real world example of a generative model is its use in image generation, specifically for creating realistic human faces. The objective here is to generate new images of human faces that look authentic. To achieve this, a generative adversarial network GAN is trained on a dataset of human faces to learn the underlying data distribution. The GAN consists of two components, the generator and the discriminator. The generator's role is to create new images, while the discriminator evaluates these images to determine whether they look real or fake. This competition between the generator and discriminator helps the generator improve until it produces high quality, realistic images. These generated images have numerous applications such as use in media production, gaming, or data augmentation, where they provide realistic data for training other machine learning models. This ability to create lifelike images makes generative models extremely valuable for creative and practical purposes. 7. Combining discriminative and generative models. In certain scenarios, combining discriminative and generative models can lead to even better results. For example, in semi-supervised learning, where only a limited amount of labeled data is available, generative models can be used to generate additional synthetic data. This newly generated data can then be used by discriminative models to improve their classification performance. Essentially, the generative model helps to create more training examples, while the discriminative model focuses on accurately assigning labels to the data. This combination of generating new data and classifying it allows the model to learn more effectively, often resulting in improved overall performance. For instance, in a task where there aren't available images to train a classifier effectively, a generative model could create additional images that discriminative model can use to learn better. This approach makes the most of both model strength generation and classification, leading to stronger results in challenging learning scenarios. Combining discriminative and generative models offers several benefits that can greatly enhance machine learning tasks. One major advantage is enhanced performance by leveraging both the strengths of generative models, which understand the data distribution, and discriminative models, which accurately classify data. The overall accuracy of predictions can be significantly improved. Another key benefit is better generalization. Hybrid models, which use both types of approaches, tend to generalize better to new unseen data. This means they are less likely to overfit and can provide more reliable predictions in different scenarios. Additionally, utilization of unlabeled data becomes more effective when generative models are used to make use of the unlabeled data that is often available in abundance. By generating new examples from this unlabeled data, these models help provide more training material for the discriminative model, which in turn perform. This combination of benefits makes hybrid models particularly useful in cases where labeled data is limited or when there is a need for highly accurate predictions. That wraps up our exploration of discriminative versus generative models. We've seen how discriminative models focus on classifying data while generative models go a step further, learning to generate new data. Both types of models have their strengths and are crucial depending on the task at hand. If you found this explanation helpful, don't forget to like and subscribe for more insights into AI and machine learning. Thanks for watching, and we'll see you in the next video in our generative AI series.